All right, so today we're going to talk about 18.1. And 18.1 is basically we're going to talk about static electricity. And charge. It looks like I misspelled it, but I don't think I did. Oof, that is not a good plus sign. Plus charge. And so just to kind of review that, opposite charges attract. So if I have a positive charge, that's going to be attracted to a negative charge and vice versa. So opposites attract. Oops, forgot a letter. Attract. I don't think there's two T's in that. I need spell check for Canva. Or I think is it CK? Attract? Attract? No, I spelled it right. And then like charges. Very excited that I was able to spell those words. 7 years of college. They repel. So if I have a negative charge here, that's going to repel away from another negative charge. Right? So opposites attract. And then if I happen to have a positive charge, that will repel from another positive charge. So like charges repel, right? And we teach this to you guys at a very early age. And so what does that mean with regards to electricity? Well, electricity, static electricity and other electricity has to do with charges. Now I could probably, let me zoom in on this a little bit so you can see what I'm talking about. So here, let me change that color to red. Okay, and we'll put that back over here. So because it's hard to tell, but this is positive charges, right? So this is a positive charge. This is a negative charge. This is going to have an attraction to this. So these are going to attract. This is positive. This is positive. So they're going to push away from each other. So this would repel. And so I misspelled the word repel. A lot of pressure doing the spelling and writing and drawing. And these are just two glass rods. And this is, it looks like a Kleenex, but usually we like to use a glass rod and fur. And we'll do this in class at some point in time. But if you rub them together, what it does is it separates the charges. One is going to kind of have an overall negative charge, and the other kind of has an overall positive charge. And we'll dive deeper into that. But now these are both negative, so this is a negative charge and this is a negative charge, and so they repel. They push away from each other. Okay. And then, well, what does this have to do with electricity? Well, let's get into it. We have to review atoms. Okay, so here's an atom. And so remember that in an atom, electrons, that's an electron. So whenever you see an E with a negative sign, that represents an electron. and electrons have a negative charge. Okay? Now, way inside here, the little, I don't know if it's purple or green or what it is. I don't know. We'll pick green. Green represents protons, and those are usually P with a plus, and that represents a positive charge, so that would be what we call a proton. And those are in the nucleus, right? And that will have a positive charge. And then because the protons are next to each other, they can't really touch each other, because if you have two protons next to each other, they'll push each other away. So they almost need a buffer. And the buffer actually has no charge, and those are neutrons. Oh, I should have matched the colors here. Let me go back and match the colors. Let's do this. And so, and I'm not quite sure, I might be off on my color scheme, but we'll make the purple neutrons. Those don't have a charge at all. It's really hard to spell all this stuff. Neutron. So we don't care so much about the neutrons, but we're really going to focus on positive and negative charges, protons and electrons. Okay? So these things like to be balanced. The nucleus doesn't really show this, but really for an element or an atom to be what we consider balanced, you usually have the same number of protons and the same number of electrons. Now, is that how it is in the real world? No, sometimes an atom will have an extra electron, or sometimes it's missing an electron. And then that's, that's stuff that happens. Now, this is the Bohr model, right? And so sometimes it's referred to as a planetary model, where we say that the electron goes into an orbit around the proton. We know that it's actually slightly different than this, but this is a great concept to help us understand how things are going, right? So the charges of electrons and protons are identical in magnitude but opposite in sign. And so furthermore, all charged objects in nature have integral multiples of this basic quantity, meaning they're made up basically of the same charge. So usually charges are formed by combinations of electron and proton, and so if we were to put a number on this charge, the basic charge for either one of these protons or neutrons would be, and it's lowercase q, 1.60 times 10 to the negative 19 coulombs. Okay. Coulomb is just a scientist that did a lot of work with charge. Oops, I misspelled his name. So obviously we have units, and you could convert this to joules and stuff. So, but anyways, basically, a proton has a positive of this, right? And an electron would have a negative. So technically, you could think of this as positive or negative, depending on if it's a proton or a neutron. So then the other thing that we can consider is the number of protons needed to make a charge of 1 coulomb. Okay. So this is a little bit trickier. So let me write this out. I'm going to say the number of charges actually I said that wrong. The number of protons needed to make 1 coulomb, right? Because this is, by the way, this is a very small number, right? This is a crazy decimal. So I would do, this is just unit conversion. I want 1 coulomb, and then I'm going to multiply that by a conversion factor. So remember that 1 proton has a charge of positive 1.60 times 10 to the negative 19 coulombs. So I'm going to make a conversion factor. Since I have coulombs here, I have to put coulombs in the bottom. So I have 1.60 times 10 to the negative 19 coulombs is equal to 1 proton. So then coulombs cancels the coulombs. And then when you do the math on that, it tells you a very specific number. So I would have, in other words, if you take 1 and divide it by 1.6 times 10 to the negative 19, you end up with 6.25 times 10 to the positive 18 protons. Now this is based on charge, because the mass for a proton is completely different than the mass for an electron. The electrons are very tiny when it comes to mass. Protons are way bigger. Okay, so now if I wanted a negative 1 coulomb charge, which is possible, you do the exact same thing, except you would have 1 electron is also equal to negative 1.6 times 10 to the negative 19 coulombs. Again, the coulombs cancel out. And then your final answer would tell you the exact number, which is the same. 6.25 times 10 to the 18 electrons. Okay. All right. So in nature, electrons and protons, they carry positive and negative charges. Protons carry an equal magnitude in charge. We call it positive. This is just something that we assign to it, right? This is all human construct, right? We're saying that there are things that exist that can have an attractive force or a repulsive force. And so we call one positive and we call the other one negative. Batteries operate this way, electricity operates this way. And then we've gone so far to determine that protons have this positive charge and that electrons have this negative charge, and then we notice that they're balanced. And this is all verified. So electron proton charges are considered fundamental building blocks, since all other charges are integral multiples of those carried by the number of electrons and protons. So electrons and protons, also 2 of the 3 fundamental building blocks of matter, because neutrons are neutral. A neutron is the 3rd and 0 charge. Okay, and so maybe we'll bring this in, but for today in the notes, there's a thing called a Van de Graaff. And let me put it. We have a Van de Graaff here. If I had more time, I would actually hook it up and let you guys charge yourselves. But a Van de Graaff machine, on the inside, has a rubber belt, and that rubber belt moves against a surface, and what it does is it polarizes charges. And so what will happen is that your hair will get these extra charges, positive and negative, but mostly positive. And so what happens is as these charges in your hair, because you'll get extra electrons and protons, they repel from each other. And when that takes place, your hair starts to stand up because your hair is very light and very thin. So when a person touches the Van de Graaff generator, and so this unit right here, this is the Van de Graaff generator, and on the inside there's like a belt, and basically the belt rubs against a surface, and that helps separate the charge. It's like when you take a balloon and you rub it in your hair stands up in the balloon. Basically, we're kind of forcing the charges. But when you do this, when you touch a Van de Graaff machine, some of the electrons are attracted to the generator, resulting in positive charges, causing your hair on your hand to stand up. So this one is going to accept negative charges. So you start off with negative charges here, they flow down through your body, and as those negative charges leave, what remains is mostly positive charges, right? So it doesn't change negative to positive, it's just you end up with more positive charges in your hair because this machine pulls away those electrons, all right? And because your hair is lightweight and mostly positive charges, it's going to repel. So the hairs move away from the surface of the scalp, they move away from each other, so your hair kind of stands up, okay? The charges in one hair are shown. So this, just imagine like this is one hair, okay? And the artist here kind of draws a picture. What you have is you have way more positive charges than you do negative charges. Now normally you have an equal amount or close to it, unless your hair is kind of staticky, but you have an equal amount of positive and negative charges, and they kind of cancel each other out within the hair. But think of if I have a positive charge here, and then I have a negative charge here, and a positive charge here, and a negative charge here, and this pattern continues throughout my hair. So this is like a human hair, right? Well, what happens is these two will cancel out. These will, I drew my thing weird. I have to decide how I want my negative charge to go. I'm going to make it look like it does in the image. So I have a positive charge, then I have a negative charge. Then I have a positive charge. And then I have a negative, and then I have a positive charge, and then I have a negative. And so just pretend that this is like a hair, right? Well, what happens is as those negative charges leave, they'll go down through your hair, ended up on the Van de Graaff machine. You have more positives. So then you have a new hair, well, it's the same hair, but I have two positive charges here, separated by a negative, and then I have three positive charges here. Well, these three positive charges are going to repel from these two positive charges. But if you keep going up the hair follicle, if you have more positive charges, then they're going to repel from each other. And so that's where the wild and crazy hair comes from, is that you end up pushing. So these three will repel against this one, but then this is also pushing against it. And then what happens is your hair just kind of stands up. Because not only do you have that hair, but you have a hair next to you like this, and it has mostly positive charges. So this hair is going to push against this one, and this one's going to push against this one. So they don't touch each other. So your hair, you get like a big afro. So an electron seems to have no substructure. In contrast, well, protons kind of do. And so what we want to do is what we have to do for electricity is understand this relationship between protons and electrons, because electrons is really the flow of electrons, right? Electricity is kind of the flow of electrons. So then electrons seem to have no substructure in contrast when the substructure of a proton is explored by scattering extremely energetic electrons from them. It appears at a point like the particles inside the proton, and I'm not going to get into the details, but there's things that cause these charges. They're magnetic spins or subatomic particles, like sometimes they're referred to as quarks, but there's other things too. Quarks are made up of spins. And so charges on electrons and protons are all directly observable particles, and these quarks or substructures charge either a positive 1/3 or a negative 1/3 or a positive 2/3. So let me show you what I'm talking about here. So when we talk about a proton, and sometimes these are referred to as spins, a proton can have a positive charge, but it's made up of different particles, right? And so these different particles can either have a positive 2/3 charge or a negative 1/3 charge. So in this particular case, I have one proton, and it's made up of 3 different particles, and these subatomic particles will have a charge. If you have a positive 2/3 plus a positive 2/3 and then a negative 1/3, these subatomic particles, if you do the math on that, you have positive 2/3 charge plus positive 2/3 charge plus of course negative 1/3. Okay, so when you do that, if you do the math on it, it ends up being 3/3, right? Which is 1 QE. Okay. Or you could think of it as 1 QC is what we were saying before. So that's your charge of 1. And then for an electron, it's different, right? So you're going to have 3 particles, and so for the electron, it would be slightly different. You'd have 2, well, that's one of your homework questions, how you figure out how an electron has a negative charge, okay? And so let's explain how that works, okay? With regards to static electricity. So in the beginning of the textbook, we talked about, if you read the textbook, we said that if you rub amber, which is like it's like a rock, it's a mineral, but it has, for the most part, 2 positive charges. Let's just assume it has 2 positive charges and 2 negative charges. So the net charge of this thing is 0. And if you rub that against a cloth that has 3 positive charges and 1 negative charge, or I'm sorry, 3 negative charges, that has a net charge of 0. So let me highlight that. So my net charge here is 0, and my net charge here is 0. So, but we have 2 positive charges. We'll just make those red. So I have 2 positive here, and then actually, see, I've already screwed up the color scheme. I don't remember what I made what. I think I'm getting this backwards from the original diagram, but we have 2 negatives, When you add them up, they're 0. And then you have the same thing over here. You have 3 negatives, 1, 2, 3. What do we do? We did this one. And 3 positives. When you add them up, 3 plus the -3, you get 0. When you rub them together, what happens is one of these is a little more accepting of electrons. Okay? One of these materials is a little more accepting of electrons. So it gives up. The cloth isn't able to hold on to the electrons as much. So it transfers these 2 electrons over here. Well, this lost 2 electrons. So when you do the math on that, this has a positive net charge of 2. This gained 2 electrons. When you do the math on that, you have a net charge of -2. Okay? And so this is what happens when you take a glass rod and you rub it against like a fur cloth, or if you take a rubber balloon and you rub it against your hair. Just the nature of the materials, sometimes some materials are a little more accepting of electrons. Electrons are a little more easy to move because they're a higher kinetic energy. Also, they're in the outer layer, right? So so when you think about that, a couple of electrons can leave because they're outside of the nucleus. The nucleus is very tight. You have a strong and weak nuclear force that holds that together. It's almost impossible to rub 2 things together and give off a proton. The only thing you have are these electrons that are out on the outskirts, so to speak. So, and you can lose 1 or 2, but you can lose enough where you change the overall charge of an object compared to another object. And so because of the way this is structured, and it really has to do with the molecular structure, how easy is it for the molecules in this amber to accept 2 extra electrons momentarily? They're not going to live there forever. As soon as they find a place that they can go to, but for right now, temporarily, when you rub them together, right? If you take a balloon and you rub it on your hair and you stick it on the wall, it'll stay there for a while, but eventually the wall absorbs the extra electrons, right? Or they find a home. And actually, the wall is the reason the balloon sticks to the wall is because the wall is somehow grounded, and so the wall kind of has a positive charge, and it's draining off those extra electrons. Okay. Anyways, so then let's talk about the conservation of charge. So. Oops, wrong thing. Well, we've observed that a lot of stuff is conserved. So there's this law of conservation of charge, right? So then in more exotic situations, such as in terms of like a particle accelerator, the mass of an object, or the change in mass, is equal to the energy of the object divided by c squared. And if you're wondering why that kind of looks familiar, you ever hear of this equation? Where this is the energy. Oh, I hate when it does that. And this is the mass of the object. And this bad boy right here is the speed of light, which is 3 times 10 to the 8 meters per second. So what this means is when you have a particle and it collides with each other, the mass can actually be broken down into the electrons and the protons, because essentially what happens is you have a proton and you have a bunch of protons in the nucleus of an atom. And then you also have the neutrons in the atom, right? Which I can't remember what color we made those. I think they were orange or red. We'll make them orange. How about that? Well, it's not going to cooperate with me, so we'll do this. Okay, so this is the nucleus of the atom. And then I think we did purple. And then you have a bunch of electrons that are orbiting. Okay, and so what a particle accelerator actually does is it takes a proton, one proton, or sometimes they use beta particles, but most of the time they take one positively charged proton, and they use magnets that have tons of, it has a positive charge. They orientate the magnets in a way that you have a positive charge here, and it accelerates this proton. This proton collides into the nucleus, and then it just breaks the whole thing apart. So then what happens is after the collision, you have these protons. It's a miniature nuclear reaction, but those protons go flying everywhere. And they collide into other protons from other nucleus. But there's so much energy. This energy is so high that it literally breaks the protons and the electrons into these little charges here. That's how we know quarks exist. We blew up some protons to see what was inside. So imagine something made with Legos and you throw it against the wall and it breaks into the individual pieces. It's basically what particle accelerators do, okay? And then the mathematical relationship is this. Also in a nuclear reaction, the reason there's so much energy released is the matter does the same thing. The matter gets broken down into little charges, but billions and billions of charges, right? Remember that it takes 6.25 times 10 to the 18 protons to make one positive coulomb. And so, you know, Avogadro's number is a very big number, right? It was at 10 to the, what's the power of that, 22 or something, or 6.22 times 10 to the whatever. So there's a lot of and that's just 1 gram, right? Based on the molecular mass. You got to do the conversion, but you guys know what I'm talking about. So we're talking trillions and trillions of charges that escape. But really what's going on is this matter gets converted into energy, and that energy is a measurement of charge. Also, the mathematical relationship has a lot to do with the speed of light. So what does that mean? Well, you can even create objects. So after that particle acceleration occurs and you have the collision, and here's a different type of illustration if you want to take a look at it, and I'll blow it up so we can see it better. So you can have energy hit something that has a mass, and you can break something up into smaller particles. You can have an electron that has a negative charge, but you can also have what we call an anti-electron. It's the same mass as in the electron, but because the charges have been changed, now it's a positive. So before you hit this particle, the charge could be net zero. So you could do this with a neutron, right? Now mathematically we'd have to check out all the charges, and that's a little more complicated. But if you hit something with enough energy, it could split up into these two things. And so the conservation of charges, I had a neutron in the beginning that had 0 charge, and then I hit it and split it up into two things that also had a net 0 charge. But what it splits it up is into positive and negative charges. And so you could do a similar thing where you take, if you take a negative electron, and this is why it's called an anti-electron, which is an electron, same mass as a negative electron, but it has a positive charge, right? And you collide them. Well, what is their charge in the beginning? Well, this is a positive and this is a negative. If you add up the total, it's 0. When they collide together, what would you have? Probably like a neutron, or it could just be raw energy. So a nuclear reaction, this happens a lot too. So like a nuclear bomb does this. A nuclear generator creates a lot of heat and energy. That's where the energy comes from. So this is one way to do it, right? And then those two particles at some point in time will collide into each other. And so in either case, the charge is conserved. Okay, it doesn't change. So let's look at this in a little more practical sense. So I'm going to do one example, and we'll try to figure this out. Okay. Oh, I just want to correct myself real quick. In this diagram, what we're really doing is we're converting the mass of an object into raw energy, or taking raw energy and converting it into a mass. So in this case, I just want to highlight this. In this case, we have energy, and the change in mass is, so if I have 2 electrons, the energy is equal to E divided by C squared. So there's energy that's going to come in, and you can create matter, but we haven't figured out how to do that. But what we are really good at is taking matter, right, and doing some sort of reaction and getting the energy out of it. And the energy can be usually, like a nuclear reactor, is in the form of heat. The sun does a really cool thing where it actually fuses hydrogen atoms together to make helium, and so that's one type of nuclear reaction, and then it actually splits those helium atoms into hydrogen atoms. So it's a combo. It's a fusion and fission nuclear reaction that's taking place, and light energy is released and heat energy is released, and it has a huge gravitational pull because of the mass of it. And it's an ongoing thing. So anyways, let's look at this in a little more practical terms. All right, so we're seeing all the charges. If I grab this balloon, see how I basically have a negative charge for every positive charge. And if I look at my balloon, I basically have the same thing. So I this sweater. And what happens is the balloon is very drawn to the electrons. It siphons off the electrons easy. The electrons, if you rub it up against the balloon, it's like, okay, come hang out with us for a while. And the electrons are like, okay. But now here's what happens when I put this on the wall. The first thing that happens is it sticks to the wall. Okay? But it also, why is that? Well, it repels the electrons in the wall away from the balloon. But then you have all these positive charges on the surface of the wall. Now, over time, what will happen is these electrons will, like if one of these electrons moves over from the balloon to the wall will somehow absorb them, and then if people touch the wall or something comes into contact, everything wants to be balanced. Okay, everything wants to be balanced, so it'll stay there for quite some time. Okay, let's reset. I'm going to do 2 balloons now. So I'm going to take my yellow balloon. The molecular structure of the wall, it's not really easy for the electrons to leave. But if I come over here, see how quickly that does that? Now, if I take this balloon and I get all the other charges, see how those repel? Okay. Now, it's very difficult to, I don't think you can rub those back on because you removed them. But what'll happen, there's negative charges in the air. Okay. If I wanted to show the charge differences, that's it. Right? And so what it's doing is showing me, it gets rid of these 4 negative charges that are associated with the positive. So if I show the charge differences, no, there's really no charge difference in the wall. Okay. So there's that. So hopefully you guys have done problems 1 through 4. And that's it for that section. I just wanted to go over it with you real quick.